dynamical circuits. Please take it away.
Thank you. Can you hear me? Great. So, well, thank you for inviting me to this workshop. It's been great meeting everyone and hearing all the talks this morning. So I did not get the memo about the audience being mostly theorists, and I'm an experimentalist. So in this talk, I'll be sharing about recent IBM quantum hardware progress that we've made in the recent years, and also running experiments on those hardware, and particularly QEC demonstrations using dynamic circuits. So the first natural question might be, what are dynamic circuits? So a quantum circuit is a sequence of quantum operations such as gates, measurements, resets, acting on qubits. So in a static circuit, circuit, these operations do not depend on the data produced within the circuit. So typically you might have some unitary gates and then you might have a final measurement and that's it. But in a dynamic circuit that incorporates classical processing, so which could allow mid-circuit measurements, that is measurements that's done not just at the end of the circuit, but in mid-circuit. And using the measurement outcome, you can do classical calculation in real time. And then using those information, which you do a feed forward, which is the part which makes the circuit dynamic, right? So depending on the outcome of the measurement that you have within the circuit, you could act on the qubits from using those results. So what I want to note here is that at IBM, we have superconducting qubits. And superconducting qubits are great systems, which we could operate them pretty quickly, right? So we have coherence time of, say, hundreds of microseconds, and the gate time could be tens of nanoseconds to about 100 nanoseconds. 2-qubit gate measurements are usually done in sub-microsecond. So that means that when you incorporate classical communication, classical calculation, you also have to do that in the same time frame, right? In the fraction of the coherence time. So doing these dynamic circuits for superconducting qubit systems are quite challenging, but we do have added this feature, new capability of dynamic circuits. And in this talk, I'm going to mainly talk about our new paper, Encoding Magic State with Beyond Break-Even Fidelity, which was published this January. And the majority of the talk is going to be that, using a very simple dynamic circuits operation incorporated in that. And I will also share the highlight of the D equals 3 error correction demonstration we did a few years ago, along with the new results using a better device than what we did on that paper. And finally, on the IBM quantum processor development. So, encoding a magic state with beyond break-even fidelity. This work was done, led by my former colleague, Riddhi Gupta. And let's see. Okay, so I will start with sharing how we are preparing these magic states. So we heard earlier this morning as well how just having Clifford operations is not enough, right? And including a special resource called magic state could complete universal set of logical gates. So instead of, if you want to do some non-Clifford operations, rather than having the state and have the state evolved under non-Clifford operation, you could use a magic state, and with some simple Clifford entangling operation and measurements, you can project into the final state, the magic state that you like. You can directly project into the final state that you'd like. So this magic state distillation protocol allows you to make many copies of these noisy magic states and probabilistically prepare a high quality magic state at the end. So for this magic state input that you have to use for magic state distillation, if you can, why don't you start from a better quality input state? So the goal for work was to prepare a better quality input magic state. And the way we did that was to prepare a magic state on the logical qubit of a code. And that suppressed the error from P to P square So this, which just shrinks the size of the distillation procedure. When you have a target fidelity, when you start from a suppressed air, you have to do just less steps, less distillation rounds to achieve the target. And so there are many different types of magic states, and there are different codes. But for our work, we chose to prepare the CZ state on the 422 code. The 422 code was discussed earlier. This one is just on the physical qubit, so just a 4-qubit code. The CZ state is defined here. And we prepare the CZ state. It's an interesting state. It could be converted into a Toffoli state using just Clifford operations and Pauli measurements. And the 422 code, this was one of the early code that we studied at IBM. And also it can easily have a transversal implementation of CZ operators on our heavy hexagon lattice. So we can prepare the CZ state by measuring CZ operators on these 2 physical qubits and starting from a plus state. And you have to throw out the -1 outcome. This will project into the magic state that we want. So we can do the same for a logical subspace. So our approach, that we call it the error suppressed magic state preparation, is then done by measuring the logical CZ. Measuring the logical CZ by preparing the logical plus state and measuring the W operator, which is defined there, with the X stabilizers SX. It's conjugated by these T gates. So these SX and SZs are the stabilizer of the code, but the 422 code, it's just the wait for X and wait for parity checks. So here's the drawing of our heavy hexagon plaquette. The outer 4 qubits, 0, 2, 4, 6, are the data qubits. We have these flat qubits, 1 and 5, and then the qubit 3 is on Zilla qubit. So the SX, SZ, W operators, you can run the same circuit here just by changing the U to identity, Hadamard or T gate. So the W operator measures CZ since we prepared the logical plus state. But now the logical operators, they need to commute with the stabilizer of the code. But this W operator only commutes with the stabilizer, the SX, when SZ operator, SZ is in the +1 eigenspace. So now either you have to just post-select when you prepare the plus state, when the SZ stabilizers is in +1 eigenspace, or you could use dynamic circuits. You measure the SZ stabilizers, and then depending on the outcome, you can apply this recovery operator to always bring back to the +1 eigenspace. By doing so, it's just very simple dynamic circuit operation in real time. You don't have to get rid of the half of the measurements. So to summarize how we prepare the error suppressed magic state, you first prepare the the logical plus state. You pick the +1 eigenspace of SZ. And again, here you could do this by applying the dynamic circuits, or you could post-select. We measure the W operator, and you could only retain the +1 eigenspace of CZ. So at this point, we do have to post-select on some of the states. And then we apply the W operator one more time just to make sure we don't have a measurement error. And then we run a round of the error detection, SX and SZ. And now, so this is what we call the error suppressed magic state preparation protocol. So now let's compare this to the state preparation, other state preparation procedures. So intuitively, you might just prepare the magic state by preparing the CZ state on the physical qubit. And then you could encode into your target code, the 422 code. So to have a fair comparison for our standard way of magic state preparation, we also added a round of error detection. And then note that the unencoded CZ state preparation is just done on 2 physical qubit. It's just a single controlled Hadamard. It's a very simple circuit. So if you want to compare what you are preparing with the encoded state, it's a pretty difficult circuit to beat, right? It's pretty simple. The encoded states have a lot more steps in. So how do we verify the state that we prepare? So we introduce a logical tomography, which is a fault-tolerant method to measure Pauli coefficient of the logical states. We have 7 unique circuits that we run, to measure the 15 poly coefficients. To the left side, there are 3 different circuits that produces 9 coefficients, and to the right, there are two other circuits that you could you run to get these 6 other coefficients. Note that the right side is a lot deeper circuit, having some of the Y operators. And now we could also compare this with the typical physical state tomography, which is done on 4 physical data qubits. You just apply single qubit rotations on the 4 data qubits, and you require 81 total unique circuits to run. So we can now compare the fidelity that we obtain from both logical tomography and physical tomography. So the results that we have here, let's start from the red unencoded results, which is just on the 2 physical qubit. In the graph, the x-axis, the y-axis is the state infidelity, and the red line there is showing the minimum infidelity that we got from this single device. It's a 27 qubit device. There are 28 different pairs of 2 qubits that we could choose from. We run this unencoded state, magic state preparation on all of them, and this is the minimum infidelity that we could get. And on the same device, we choose 7 qubits to encode the 422 code. And in the standard procedure, this is in the orange data point. We have results from the logical tomography and the physical tomography. And the results are very similar, as it should be, but the results are above this green line. And the green line is showing the average infidelity from all the 2 qubit unencoded state that we prepared. And finally, the blue points are using the error-suppressed magic state preparation. And again, it's comparing both the logical tomography and physical tomography using post-selection. They go below the infidelity of the unencoded magic state preparation. And then also to the very left, which is using feed-forward or the dynamic circuits, which we wanted to compare how well we do with the feed-forward operation versus a post-selection. And for that case as well, we are beating the best unencoded physical magic state preparation that we could do on the same device. So just to show why we might want to do this feed-forward, is that as you see on the left side, these are points from all the 7 different logical tomography circuits. And if you look at the blue shaded region, you see the acceptance rate of how much data you obtain by using feed-forward is about the double if you compared to if you hadn't done the real-time feed-forward. So just as to summarize, we demonstrated the error-suppressed magic state preparation exceeding the direct preparation of physical qubits. So you saw how simple that the physical qubit circuit is. So we were pretty excited to see that the state that we prepared using the 7 qubit with that pretty deep circuit, using both logical tomography and physical tomography, we were beating that fidelity. And I won't go through all these points, but in our paper, we also go further into details about how we use error mitigation on the state tomography. And on the main paper, we did not apply any readout mitigation, mainly because there are ways to kind of screw up the results of the state tomography by not applying the correct measurement error mitigation, the readout mitigation. So sometimes you could overcorrect it, sometimes you could undercorrect it. So we wanted to have a fair comparison between all the way that we prepared the states. So the results that we have from the main paper, we did not apply any error mitigation, but there's a lot more details on that in the supplement of the paper. So this experiment was done on IBM Peekskill, which is a 27-qubit Falcon R8 processor. And it was just using 7 of these qubits highlighted here. And on the same device, we had done a D=3 error correction demonstration a few years ago. So I wanted to share some results from that paper. And the paper was, So I think Andrew discussed about the heavy hexagon compass code earlier. So I don't have to go through this slide, I don't think. But just to review, we have one type of the checks as a Bacon-Shor stabilizers, and the other is surface code. And I think this color scheme is probably doing the Z error on the surface code, which Andrew did say, but where our systems had more phase errors, and which we wanted to make sure we could correct with the surface code. So the experiment that we did for this paper was to prepare a logical state by performing one round of either an X or Z stabilizers, starting from either old 0 or plus state. And then you run n rounds of stabilizer measurements. So each round consists of both X and Z checks. And then you finally do a logical state readout. So here is a sample of the circuit that we run with X stabilizers and Z stabilizers. So each round on this IBM peak skill, it took about 5 microsecond to, 5 microsecond for each round of stabilizers. And here is a very dense summary page. I wanted to put all the highlights of the paper in one slide because I wanted to focus on the next experiment. But the main points were that we found a lot of leakage in the system. And as you see in this plot, the bar plot, this is showing the leakage, how much leakage post-selection we actually ended up having to do. And when we look at the leakage rate that's coming from the measurements during the circuit, and also we had, which is plotted in red, and we also see a lot of leakage in the 2-qubit gates. So those are plotted in blue. And when we actually added up for each round, it matched pretty well with how much data we thought that was leaked throughout the circuit. So it's nice that it matches. It's not that great that we have a lot of leakage. But to the right of that plot, you see the two different curves in the two different colors are showing how much improvement we get by doing a leakage post-selection of the data. And also, another thing to note is the blue curve, the data of the X basis, and the red and Z basis. So the two are about factor of 2 difference in the error per logical rate, error per logical error, the logical error rate. And then finally, using the raw data, so not the raw data, the leakage post-selected data, we also compared different decoding schemes. So for the matching decoder, we looked at different weights. So we used uniform weights, analytical weights we got from Pauli propagation. And then we also included soft information by looking at some of the measurement bias. So if you have some measurement that are more noisy, you use these weights as an information added into the analytical decoder. And then finally, we compare that to the maximum likelihood decoder. And we see the improvements in the logical error per round by including more of these information. So this is a very dense, again, summary of the paper. And now we run this exact same experiment on our newer device called Egret, which has a different architecture. So the previous device, Falcon devices, they had a gate called the cross-resonance gate. The Falcon devices are transpon qubits. So this is going into the hardware discussion, but these fixed frequency transpon qubits, the previous devices, these always had this always-on coupling. So it's very easy to operate, but at the same time, because of the always-on coupling, there's a lot of crosstalk. So this newer version of Egret has a tunable coupler. So that means that you could have an on and off state of the coupling. So that reduces a lot of the crosstalk. So if you look at the gate errors between Falcon R8 and Egret R1, the 2-qubit gate error has decreased quite a bit. But if you look at the circuit, the 2-qubit gates from the tunable coupler device are much faster, but the measurement time is pretty similar to what we had. So the majority of the circuit, now the total circuit length is about 3 microseconds for the X and Z checks, but it's really mainly from the measurements. So now when you look at the plot, this is only using a uniform decoder. We did not evaluate using different type of decoder for this experiment. You see that now with the X basis and Z basis, the results are very similar. And then the results are very comparable to the Z basis results we had from peak skill. And then we did see improvements when you do some leakage post-selection. I don't have the plot here, but the leakage rate was a lot less compared to Falcon R8. So there are still leakage from the measurements, but the leakage from the 2-qubit gates has reduced quite a bit. So now here I'm showing the IBM's roadmap. So IBM has been having this development roadmap since maybe 2019-ish. And this recently, we've added this innovation roadmap as well. So on the top, there's a development roadmap, where here you see the Falcon, the 27-qubit Falcon, and the dynamic circuits capability that was introduced at the end of 2022. And this is what we had run the experiments with for the encoding magic state and also DCOS 3 experiment. And now the core processor at IBM is the 127-qubit Eagle device. This is an extension from the Falcon device, so it has all the cross-resonance gate. And if you look at the bottom of the page and the innovation roadmap, we have gone from Falcon to Hummingbird, Eagle, and Osprey and Condor. We've gone to at the end of last year, we demonstrated an over 1,000 qubit device, a Condor device. And these are all based on a cross-resonance gate. So at IBM, we've been working on trying to scale the number of the qubits. But as I brought up earlier, eGrid wasn't on this development and innovation roadmap, but I just added right there on 2022. So going down is the increasing the performance, right? So on the top row, you are scaling the number, but then moving to a different type of coupler, you're also improving the quality of the device. So now we have eGrid, and then this Heron processor with the 133-qubit device is going to be, sorry, I didn't circle it, but on the development roadmap for this year's processor, the focus is going to be the Heron processor. So just to briefly discuss the Heron processor. Heron processor is a 133-qubit processor, slightly bigger than Eagle, but it's the same heavy hexagon lattice. It has fixed frequency transmon qubits with tunable coupler architecture, similar to the eGrid device that I talked about earlier. The gate error are much improved compared to the Eagle devices, but the big part is that it has significantly reduced crosstalk. And on top of that, the gate time of these devices, on the Eagle devices, we had 500 to 600 nanosecond gates, the 2-qubit gates, and now down to about 90 to 100 nanoseconds. So it's much faster. And you can see the gate performance in this plot. So here is the average gate error of all the pairs. Blues are the Eagle processor with cross-resonance gate. And then the pink purple is the new Heron architecture. As you see how the Heron has much lower 2-qubit gate errors. But also something to note here is that there are 2 lines for each processor. One is benchmarking the 2-qubit gates in an isolated way. You could either benchmark the 2-qubit gates just by itself, or you could apply all the 2-qubit gates that you could together and then benchmark that way. On an Eagle processor with a lot of crosstalk, you see that big difference on the blue curve when there's a crosstalk, the big crosstalk. But on the Heron processor, there is still the crosstalk, but this difference is much smaller. So now, what's next with Heron? On our development roadmap, we have Heron for this year, and then from then on, we have these Flamingo devices. So Flamingo is a close cousin to a Heron device. It has a few extra more qubits, but it's a similar architecture as Heron. And what we are working on is to have these interchip couplers to Heron that will make it the Flamingo. So the Flamingo is going to have a coupler called L coupler. Here, I think I might have a picture of that. Yes. So here you see that this year the quantum team has been working hard on implementing these L couplers. You see this microwave cables that's connecting the two chips. So these are going to be the workhorse of the IBM quantum devices for the next few years. And I want to show this development work, this roadmap one more time, and just highlight where we are aiming for a system with full error correction. That's slated for the end of 2029, right? And then just looking at the innovation roadmap, we want to have all these couplers that we mentioned, these couplers that would allow us to have non-nearest neighbor coupling. And these have come up in the previous talks with the bivariant bicycle code. So this is very important for us as we scale up the devices. We don't want to just scale in the planar manner. As we heard, the surface code, heavy hex code, it's not very efficient in number of qubits, right? Like it will be very difficult to make many, many qubits to get to the error rate that we want. So as the theory team make a new progress in coming up with new codes, the hardware team is also working towards allowing those codes to become real architecture. Well, that was it. Thank you for listening. I'll take any questions.
We have time for maybe 2 questions.
Thanks for the very nice talk. I have a question regarding this dynamical capabilities, where you showed this, as you said, pretty basic example to do or not do a bit flip. Can you comment a bit more on how much more complicated it would be to call entire conditional subcircuits? You know, if you think about doing a number of error correction rounds and perhaps another round or not, and also what the challenge is with doing actual in situ decoding.
Right. Yeah, thank you for the question. So for this example, I only showed how you could do the single qubit rotation based on the measurement outcome. We could do a lot more than that currently on Qiskit. You could write with the QASM3. Not all the operations that you could write on this open QASM3 language is currently available, but a lot of the features are there. I don't think there's a way to do a full error correction round at the moment with the way it's implemented, but it's pretty flexible in a way that it doesn't have to be just single qubit. You could have like XOR, not just from single qubit measurement outcome, but you could do XORs, you could do some parity, and then some gate application on other qubits. For actual decoding, I think you would need to have the decoding on an FPGA and do it that way. So it would be a little bit different than right now, right? Like we can't, some external user cannot do this decoder and then apply on the error correction. But a simple dynamic circuits operations, any users who wants to use IBM device right now could write a simple program to apply these bit flips and some property flips.
Hey, Maika, excellent talk. One question I kind of had was looking at the peak skill versus Prague comparison. It looked like Prague was really fantastic. Like the 2-qubit error distribution was far to the left. You mentioned it had a lot less crosstalk. I think you said there was reduced leakage. And I was wondering if the sort of difference in the error correction experiment, what you expected? It seemed like the error correction it seemed like it improved, but with such a processor advance, I was wondering if it improved as much as you would have expected, or if some kind of error is dominating.
So I hope that it would have looked better, but I think the big error is coming from the measurement part. I mean, as you saw it in the circuit, right? Even with the egret, with the much faster gates, majority of the time was spent on the measurement and the reset operation. So I think that's a predominant error for this experiment. And we were hoping that the phase error, that some crosstalk error would be gone. So which I think we did see by seeing both X and Z basis results to be similar.
Thank you. That makes perfect sense. Thank you.
Okay, one last question.
Hi, yeah, I was wondering if you could say a bit more what you demonstrated with the 1,000 something qubit chip. And also, when you do the post-selection with leakage, I guess you're measuring the token occupied state, and is that how you post-select?
Yeah. So maybe I'll start from the second question about the leakage post-selection. So for our experiment, how we did was we just took the IQ data of the measurements, and then we have some calibration data where we have 0 and 1 state. And we define with some sigmas, we define a blob. And we say that if it's outside a certain sigma, we say it's leaked. So it doesn't have to be 2, 3, or 4. It's outside that space, and we just threw it out. And then for the Condor, the demonstration we did was we did not deploy the Condor devices. We showed last year that all the qubits were alive, and we showed that we could do some basic gate operations. I think the development that what we wanted to show with Condor is that we know we could scale up to that size, right? That's a very big engineering challenge to have that many number of qubits. So even though we did not release to clients how to use the device, that was a demonstration we had. The one size smaller Osprey, the 433 qubit device, although now it's not available anymore, but we did have that available to clients for a certain time. I want to say last year or 2 years ago. Yeah.
Okay, in the interest of time, let's take the other questions offline. Let's thank Maika again. And we have a short coffee break. So